morning students, welcome back to my next lecture. So in this lecture we will learn about moment of couple. So first of all we will consider a metallic rod, and the rod is pivoted at a point at its center, and we mark it as O, and the ends are marked as A and the other end is B, and we are applying force at point A downward, whereas the same equal amount of force is acted at point B in upward direction. So here the perpendicular distance between the two point of action of force, that is from A to B, is considered as distance D, and the force is considered to be F. So these two equal and opposite force are acting on the two ends of the rod, which makes the rod rotate in anti-clockwise direction. As this force is able to turn the rod in this way, similarly this force also. So both forces are responsible to turn the rod in anti-clockwise direction. So first of all we will calculate the moment of force at point A. So it will be force multiplied by the distance from the pivoted point. So F multiplied by distance, that is OA. Similarly, and this moment is anti-clockwise, so we will write here anti-clockwise. Similarly, moment of force at the end B. So if we talk about the force at end B, similarly we will find force multiplied by the distance of point B from the pivoted point, that is OB. So since this force is also acting in this anti-clockwise direction, we will write anti-clockwise. So if we talk about the total moment, that is total moment of couple, or you can say in other words the total moment of both the forces. So we have to add the moment of both the forces, that is F multiplied by OA plus F multiplied by OB. So here in these two parts we can take F common, so it will be OA plus OB, and from the figure we can say this OA plus OB will be AB, so it is force multiplied by AB, and we know the distance AB is D, so it is F multiplied by D, and the direction is anti-clockwise. So from the figure we can say that the two forces are responsible to turn the rod in anti-clockwise direction. So this is called the moment of couple. So here point to be noted that the distance between the 2 points where the forces are acting is called the couple arm. So this here AB is considered as couple arm, and we can consider either of the forces as both the forces are of equal magnitude. So in other words we can say that total moment of couple is either force multiplied by the couple arm, that is AB. So now we will learn about equilibrium of bodies. So when a body is free, that is it is not pivoted at a point, so when force applied on it, it produces translational motion. Similarly, when a body is pivoted at a point, then force applied on it produces rotational motion. Suppose we have a body and the body is free, so when force is applied on the body, it experiences translational motion. Similarly, suppose we have another body and the body is pivoted at a point. So when the force acts on a body which is pivoted, then this body will experience rotational motion. But there are circumstances when we apply a number of forces such that the resultant of all force is zero. Like in this body, suppose we have another body, and when we apply a 10 Newton force along this side and a similar force, that is 10 Newton, from this side, so in this case what will happen? The body will remain at its position. So that means we can say that the body is in equilibrium. That is, the body will not change the state of rest or linear motion of the body. Now suppose we have a rod which is suspended from its midpoint, or you can say the rod is fixed or it is pivoted at its midpoint. So when a force at a distance of a fixed unit, that is say 10 centimeter, when a force of 10 Newton acting at a distance of 10 centimeter from the pivoted point, here also at a distance of 10 centimeter, a same force, that is 10 Newton, is acting downward. So what will happen? This force is producing a anti-clockwise moment. Similarly, this force is able to turn rod along this way, so that is, this is creating clockwise moment. But here anti-clockwise moment created is same as the clockwise moment. So what will happen? Here the algebraic sum of moment of all the forces about the fixed point is zero, so they do not change the rotational state of the body. Then the body is said to be in equilibrium. So here the body is said to be in, these two bodies both are in equilibrium. Now I will define what actually equilibrium is. So when a number of forces acting on a body produces no change in its state of rest or of linear or rotational motion. Here you can see that in both the figures the body is remained at its position. It is not changing its position. Here also the body is not rotating despite the two forces are acting on it. But the forces are balancing each other. That is, the moment of force both have balanced each other, so the body would not rotate. So here is the definition: when a number of forces acting on a body produces no change in its state of rest, of linear or rotational motion, then the body is said to be in equilibrium. So here you can see the bodies are in equilibrium. Why? Because the forces have balanced each other, so the body will remain at its position. Now we will learn about kinds of equilibrium. So there are basically two types of equilibrium. First one is the static and the next is the dynamic. So here static equilibrium means when a body remains in the state of rest under the influence of several forces. Means here suppose there is a body and this body is placed on a tabletop and it is pulled by two forces and they are opposite in direction. So these two forces are equal in magnitude and opposite in direction. So what will happen? The body is pulled by equal force along both the direction. So there is no net horizontal force. acting on the body, so the body will remain at rest. So this is the case of static equilibrium. So there is another example, a book. When a book is placed on a tabletop, okay, and then here the downward force, that is weight of the book act by it, is same as the normal force acting on the book by the tabletop. So here the weight of the book is balanced by the normal force acting on the tabletop. So the book is said to be in static equilibrium. Why? Because there is no net vertical force acting on the body. Now if we take the example of a beam balance, like when the beam is balanced in a horizontal position, we can see the figure like this, something. So from this figure we can say that here the weight placed on this left side pan is balanced by the weight placed on the right hand pan. So the moment, that is the anti-clockwise moment generated by the body placed on the left pan, is same as the clockwise moment produced by the weight placed on the right pan. So here what happens, there is no net moment, that is the clockwise moment is same as the anti-clockwise moment. So there is no rotation of the, that is there is no turning of the beam balance. So here again we can say that here the left pan is balanced by the right pan, or you can say the right pan is balanced by the left pan, that is there is no rotational motion. So the beam balance is said to be in static equilibrium. Now we will talk about dynamic equilibrium. So when a body remains in the same state of motion, translational or rotational, under the influence of several forces, the body is said to be in equilibrium, dynamic equilibrium. That is, let's suppose there is a raindrop who is falling downward. So when a raindrop is falling downward, so here the weight of the falling drop is balanced by the sum of the buoyant force and the force due to friction, or you can say in other words the viscosity of air. So here the weight of the raindrop is balanced by the buoyant force plus the viscosity of air. So these two forces combine together to balance the weight of the raindrop. So what happens? There is no net force acting on the raindrop. So what happens? The raindrop falls with a constant velocity. That is, during fall of raindrop there is no acceleration due to gravity. That is, it falls with a constant velocity. Now we will learn about what is the condition for equilibrium. So the first condition for equilibrium is the resultant of all forces acting on the body should be 0. That is, when a number of forces acting on the body, so the resultant force should be equals to 0. Like we have discussed also that suppose there is a body and a force acting along this direction and another push force is acting from this direction. So both these forces are counteracting, that is they are balancing each other. So what will happen? There is no net displacement of the body. So the next condition for equilibrium is the algebraic sum of moments of all the forces acting on the body about the point of rotation should be 0. As we have discussed, like there is a suspended body and we are exerting a force at this point and another force is exerted at this point. The forces are such that the moment of force produced by this at this point would be same as the moment created at this point. So the body will not rotate at all. That is the sum of moments of force created by force F1 and force F2 is 0. That is, it is a vector quantity as it is turning anti-clockwise and it is responsible to turn clockwise. So here anti-clockwise moment is same as a clockwise moment. So there is no net rotation of the body. Now we will discuss about the principle of moments. So according to principle of moment, if their algebraic sum of moments of all the forces acting on the body about the axis of rotation is 0, then the body is said to be in equilibrium. So the principle of moment is sum of anti-clockwise moments is equals to sum of clockwise moment. So we can consider the example of beam balance, or you can say the physical balance, which works on the principle of moments, that is anti-clockwise moment should be same as the clockwise moment. In only that case the physical balance remain in a horizontal position. So there is a verification of the principle of moment. Suppose we have a scale or we have a rod with a gradations over it. So a weight is suspended through a spring at a point, say A, and the weight is W1, and another weight at point B is suspended through the string and it is W2. Now we will observe that the rod will start tilting in some direction, whether in the clockwise direction or in the anti-clockwise direction. So now what we have to do, we have to just adjust the masses. We will adjust the masses such that the rod remains in the horizontal section or in the horizontal position. So after adjusting, let the weight W1 is at a distance L1 and the weight W2 is suspended at a position L2 from the suspended point, or you can say it is a pivoted point. So what will be the anti-clockwise moment created by W1 weight? So here clockwise moment will be here W1 weight is creating anti-clockwise moment, whereas W2 weight is creating clockwise moment. So clockwise moment created by weight W2 is equals to, here weight is the force, so force is represented by W2 multiplied by the perpendicular distance from the pivoted point, that is L2. And if we go on finding the anti-clockwise moment, it will come W1 multiplied by the distance L1. So we will observe that the value, that the numerical value which comes on multiplying W2 with L2 and W1 with L1 will be same if the meter rule is in balanced position. So from here we can conclude that here in equilibrium position W2 multiplied by L2 should be same as W1 multiplied by L1. So this is the condition, that is clockwise moment should be same as the anti-clockwise moment, and this verify the principle of moment. That means that to balance a meter rule we have to produce clockwise moment that should be same as the anti-clockwise moment. Now I will discuss how to solve the numericals based on a uniform meter rule. So there is a question. A uniform meter rule rests horizontally on a knife edge at 60 centimeter mark. When a mass of 10 gram is suspended from one end, draw diagram of the arrangement. Question 1. At which end must this mass be suspended? What is the mass of the rule? So the question tells there is a uniform meter rule. So we will draw one uniform meter rule. So this uniform meter rule is balanced at 60 centimeter mark. So this we have to consider the entire length is 100 centimeter. So this midpoint will be 50 centimeter. Since it is balanced at 60 centimeter mark, so we are considering as a knife. So this meter rule is balanced at this position. So this is 60 centimeter mark. So can you just tell me in which direction the rod will tilt or the meter rule will bend? So obviously this portion is more, so weight of this 60 centimeter mark will be more than this 40 centimeter mark. So obviously this side the weight is more, so the rod will tilt along this direction, that is it will bend in anti-clockwise direction. So the question asks in which direction, at which end you will place a mass such that the rod will be balanced or the meter rule will be balanced. So obviously we have to place another mass in this direction such that the mass will generate a clockwise moment, and this clockwise moment should be same as anti-clockwise moment in order to balance the uniform meter rule. So we will consider this end as A and the other end as B. So from the figure it is clear that we have to suspend the mass given is 10 gram. So we have to suspend the mass at this point B. So this is the mass suspended and its mass is 10 gram. So do you know at which point the weight of the meter rule will act? So obviously we know that weight of a body acts at the center. So we are considering let the mass of the uniform meter rule is capital M. So here the weight will act at 50 centimeter mark vertically downward, and it is mg. Please make it clear, here m is mass of the uniform meter rule, whereas g is the gravity, that is mg. Here also 10 is the gram and g for gravity. So weight is mg and here weight is 10g. So whatever the anti-clockwise moment generated by the weight of the meter rule should be balanced by the clockwise moment produced by the weight suspended at point B. So here from principle of moment, so anti-clockwise is produced by the weight of the meter rule. It is mg multiplied by the distance from the pivoted point. So it is 60 centimeter minus 50 centimeter. And here the clockwise moment is produced by this weight suspended, 10g multiplied by the distance, that is 100 minus 60 mark. So this mg multiplied by 10 will be balanced by 10g multiplied by 40. So 10 will be cancelled, gg will be cancelled. So from here we can say that the mass is 40 gram. So the mass of the uniform meter rule is 40 gram. So go through the questions provided. In case of any query, just contact me.